Will we be done by 11:45? You know, there's a fairly good chance of that. I know you want to go for 2 hours, but, you know, we might get done by then. Oh, right when I took attendance, someone else showed up. How do you like that? I think everyone's here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, there's one person missing. Who's missing? Who is it? Tell me. You're right, Guinevere. Good for you. Bonus points. All right, what state of matter is this substance in? This is your first question. Do you guys even know what the states of matter are? What are they? Solid, that's one. What other ones are there? Ooh, someone's texting on me. Oh, it's T-Mobile. Thank you, T-Mobile. Liquid and gas. Nice work, nice work. Some of us have more gas than others, am I right? Solid, liquid, gas, and plasma. Exactly, Shay. I was just going to say, there's also a state of matter called plasma, which is when there's so much energy that electrons cannot stay attached to protons, and virtually all of the atoms are then ionized. And so it's kind of a unique state of matter, which isn't really like any of the other three. So anyway, what state of matter do you think this substance is in that is being held in the hand of this person? Well, semi-solid just means that some parts of it are solid and some parts of it are liquid. So good guess, though, Harrison. I see solid, liquid. I even see gas. Solid and liquid. Yes, yes, yes. So this particular metal is actually right in between two states of matter, the liquid state and the solid state. The liquid is dripping down beginning to drip down the person's hand. Now this is a particular metal called gallium. And you see gallium has a melting point of 85 degrees Fahrenheit, 30 degrees Celsius. And the human body is just a little bit warmer than that. So as it comes into contact with the human body, it may begin to melt. Interesting, isn't it? You can see where gallium is. I hear somebody rustling around, so I'm going to go ahead and mute you, because I wouldn't want you to emit a gaseous state of matter that we could all hear, and then everyone would laugh. Of course, they'd think it was me, and everyone would laugh at me, so I guess that wouldn't be good news for anyone, would it? So we can see gallium. It looks like chrome because it's a metal, so it's shiny like most metals are. It's a good question, Guinevere. Gallium, you can see it right there, Ga. And you can see, again, trends in the periodic table. It has a low melting point, which is why it's kind of whitish in this. Is there anything nearby it that's also kind of whitish? Or maybe I should say, what's the whitest element nearby it? I would say you're right. Sn is fairly light, but it's a little bit pinkish. But the Hg, well, N also, and nitrogen is actually a gas in that state of matter, so it's purely white. But you can see that the Hg down there is also similarly just barely pink like gallium. Do you guys know what Hg is? And I ain't talking about no home and garden television, okay? If that's what you're thinking. Hg, it's actually an element that we refer to with an M. It's also the name of a planet and a god in Greek literature. Mercury, that's right. So Mercury, you may know, is liquid at room temperature. It's the only metal that is liquid at room temperature, though gallium is close. And so we used to use mercury for thermometers and things like that. So you can see there are uses for things like that. There's also mercury that you eat, unfortunately, because it gets into the food system. And as bugs eat it, and then fish eat bugs, and then we eat fish, we can bioaccumulate mercury into our bodies, yes, which drives you crazy. In fact, if you remember Alice in Wonderland, the Mad Hatter, In is indium, which is not a very common element. Hatters, people who make hats, put a lot of mercury. They used to use mercury as they were felting the hats, and it was a poison, and it would drive them crazy, and so that's why they were mad. The Hatters were crazy or mad because of the mercury they were exposed to. Anyway, that's another story for another day. So gallium, here's gallium, you can see, has 31 protons, 39 neutrons. What does that mean its atomic number is? What's the atomic number of gallium? 31, excellent. And Harrison is giving us the atomic weight, or the atomic mass, actually. He's jumping ahead, jumping ahead. Here's a gallium spoon. I wouldn't stir your coffee with it because obviously your coffee would be more than 85 degrees Fahrenheit. And as you can see, that causes problems. All right, moving right along. Oh, also, another fun fact, I forgot about this one. Gallium, when you put it like on an aluminum can, like in this case, someone dripped some of it onto an aluminum can, it actually filters into the throughout the aluminum because it basically just becomes one of the molecules with the aluminum, and it can actually soften up the aluminum can so that you can very easily then punch a hole in your aluminum can with gallium. So again, another dangerous. It makes it very soft, the metal. Yeah, get some gallium. Buy some at the store. Show me what you can do with it. I've never had any, so I don't even know. I just look at YouTube or watch or get GIF images. You guys want to see this one again? Give your mom a gallium spoon. Black market time. That's right, Joel. You kids, aren't you all bad kids that do all kinds of bad things and buy bad things? Good for you. I guess Tori and Joel, if you want to buy bad things, talk to Tori and Joel. All right, well, we're talking now about bonding. Today we're going to start thinking beyond just the simple atoms and their structure. And we're going to think about what happens when we get atoms together with other atoms and the different ways that we can do that. Now, you might think that when you're thinking of bonding, it's like atoms touching, and we talked about that already. And that's a pretty good illustration. In fact, one person in my class kind of illustrated atoms touching as chemical bonding. So you can see this person showed what a hydrogen atom looked like by itself. I need a new color here. This is not a good color. Somebody get me a better color. There we go. And an oxygen atom. And then if you put them together, like one oxygen with two hydrogens, then they share electrons, as you know, in this class. Although I think this was last year. Last year's might even been the year before. I don't know, to be honest. Sharing electrons. And that might be, in a sense, the closest atoms can get. It's not that they're actually sort of physically coming up in contact, but they're close enough that their electrons kind of buzz back and forth and are shared between them. Exactly, Shay. That is covalent bonding, which is what we're going to be learning about. One of the types of bonding we're going to be learning about briefly today. You know, in fact, we're going to learn about that, and then I'm going to look at your projects so we can see what some of you did for your projects. So, atoms touching might look like that bonding. Here's two oxygen atoms doing the exact same thing. You know that all the oxygen that you breathe is not single oxygen atoms. They are much more stable when they're bonded with each other. And so if there's ever a single oxygen atom, it's going to move around until it finds another one to bond with. And they're always going to have a covalent bond of 2. That's right, it's going to be O2. That's why you'll see that whenever people write out oxygen, they usually write out O2 because that's 2 oxygens bonded to each other, and they just follow each other around because they're bonded. Yes, Tori and Joel have not finished yet, so give them a hard time. That's how this class works. We make people feel bad until they do work. It's a very effective method. Well, that's interesting, Shay. You're exactly right. They were probably out on the black market when they were supposed to be doing their work, and they were trying to buy some drugs or some guns or something like that, and they weren't doing their homework. And now look where they're at. Ha 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 ha! You wish you were buying guns and drugs? Oh, Joel. Oh, Joel. No, you can don't. What's that? Yeah. I'm not going to be taken out onto a wild goose chase. So here are some atoms that are in close proximity to each other, and as you can see, all these atoms have no electrons in their outer shell. And bonding has everything to do with the electrons in the outer shell. That's a great question, Joel. That V stands for something, because all of the electrons in the outer shells of these atoms have vacated those atoms and are sort of moving freely in between them. So that V stands exactly for that, yes. Both Shay and Guinevere, that V is for valence electrons, and those valence electrons have left their atoms. And exactly right, Joshua, that's metallic bonding when those valence electrons are shared between all those atoms. But there are different ways that we can do that. So in metallic, it's almost like communism. Those valence electrons can go far and wide, and that's exactly why electricity flows so well, because electricity is just electrons moving through something. Well, if electrons are free to move without being sucked up by different atoms, but they're free to move around, then they're going to move very well over long distances. And that's why metals tend to be very good at conducting electricity, because those valence electrons are free to move around. And so if you put a positive charge on one side, it's going to suck all the electrons towards that positive charge. And if you can keep that moving, you can create an electrical current. Well, the way that we determine what type of bond is probably going to be taking place is by looking at something like this. This is a 3D periodic table. Now, you can see that there's a measurement of electronegativity is the third dimension here. How electronegative the different elements are. Now, electronegativity just means how greedy they are for electrons. So, if 4 is the greediest you can be for electrons, which element is the greediest element on the periodic table? Exactly right. F is for fluorine. Yeah, so fluorine is the greediest, and you can see what are some other really greedy elements besides fluorine. Maybe 2 or 3 others that are close to it. Yes, oxygen, nitrogen, chlorine. And that's exactly the reason why you'll never see those atoms by themselves, because they're so greedy for electrons that they have to share with somebody or get some electrons somehow to feel good about themselves. So, let me show you what tends to happen. What tends to happen is covalent bonding. So 2 oxygen atoms, which are very greedy for electrons, will just say, hey, let's get together. We're so greedy that we're not going to, I'm not going to give mine up, and I'm going to try to suck yours away. And then eventually they just decide, oh, we're both evenly matched. We both have the same, electronegativity. So we'll just sort of share these electrons between us, and these electrons will kind of go back and forth between the two oxygen atoms, and they'll stay close together to maintain that sharing, because they're so greedy that they're not gonna leave that other oxygen atom with the electrons. So that's covalent bonding. And it's odd, but the greediest atoms are the ones that end up sharing. Well, they can do something else as well, though, because when they meet someone who's not quite as greedy as they are, yeah, they're sort of stealing back and forth. That's one way of thinking of, maybe that's what sharing is, stealing back and forth. Then they can create something called ionic bonds. So that happens when you have someone who's very greedy, like, say, chlorine, which you remember was like right there next to fluorine, a very greedy electron, and then one on the other side of the periodic table, way over here, where these, you can see these ones way down here are, they're like 1 electronegativity, something like that. They basically can't hang on to their electrons at all. They're just sort of like your forgetful friend that leaves his shoes or his glasses or something everywhere that they go. Or someone who's kind of wimpy, like your little brother, and you can just steal stuff from him and they can't do anything about it. I hope you're not mean like that. But probably Joel and Tori are. You know how they are, right, guys? Yeah. Right. So chlorine, chlorine being very greedy, when it comes into contact with something like sodium, not very greedy, it just takes its electron, because sodium is not hanging onto it very tight, so chlorine takes it. But when chlorine does, it then has an imbalance, and this is the key to ionic bonding. Because whereas before, chlorine had 17 protons and 17 electrons, it was electrically neutral. It was balanced. 17 positive charges and 17 negative charges, right? Well, now it has one extra electron because it stole one. So now it has 18 negative charges. So now it overall has a negative charge, which is why there's a plus sign down here. And the opposite thing happens to sodium. As it loses its electron, it has one fewer, and now it has a positive charge overall, as you can see here. And so those two atoms then, even though chlorine stole the electron, they're going to be attracted to each other because one of them has an overall positive charge and one of them has an overall negative charge, and they're going to stay connected, basically. Sodium chloride. Yes, just like Shay drew there with those arrows. She's better with arrows than I am, apparently. So those are the two main types of bonding. Covalent, where you share, and ionic, where one person steals, but then that gives them a negative charge, the other one a positive charge, and so they're then sort of sucked together like two magnets. Opposites, you see, attract. Well, and then those ones in the middle that have some greediness, but not too much greediness, are able to form these metallic bonds where instead of that it can just have a single element, but it can just be spread out forever and ever and ever, and those electrons can be shared all throughout the whole area. Oh, I thought maybe Sam showed up, but it was not. And that is something you might call communism, where everyone shares everything in common. You know, the political system of communism. The idea, though it's never really worked in practice, is that everyone shares everything. The problem is we're a little bit too greedy, so it doesn't tend to work out. But everyone shares everything in common, and therefore everyone has enough. Or so we hope. So we like to think. Oh, you're welcome for a little government. So now let's look at these two types of bonds and think about their melting point. We're going to kind of forget about metallic bonds for a while. They're not as important as the other two in chemistry. So the first one here is covalent bonding. Oh, Sam showed up. All right. Samwise, you're here. So you can see two H atoms, in this case, would join together, sharing an electron to form a bond, a molecular H2. So that's covalent bonding. Now you remember sodium and chlorine, The chlorine is going to steal an electron, so it's going to get an extra negative charge, whereas sodium will then have a less negative charge, down to minus 10. And so they're going to then form this sort of lattice structure where all the chlorines will get as close to the sodiums as they can because they're attracted to those positives, and they'll get kind of farther away from the neighboring chlorines, and they form this lattice structure where it's like chlorine, sodium, chlorine, sodium, chlorine, sodium, and it keeps going and going and going. And that is how ionic bonds work. And you've already learned about sodium and chlorine and how they're both deadly. One of them is basically explosive in water, and the other one is a deadly gas. But when they get together, they're just nice and calm and peaceful in their ionic bond, and you can eat them on your food, which you do every day because you eat lots of salt. Table salt. So you can see that when water, whether it's in liquid form or in solid form, as an example, it's always going to maintain a connection to the two hydrogens are going to maintain their connection to the oxygen, whether they're in liquid form or solid form. Floor salt. That's a good one. That's a good one. That's a good one. But you can see that to melt a solid like sodium chloride, you're going to have to break the bonds. Here, you don't have to break the bonds because those bonds just stay the same. You just have to separate the water molecules from each other, right? To create a liquid where the molecules are free to move around. But over here, you actually have to separate each positive charge from each negative charge. You're going to need a lot more energy to do that. You're going to have to break that bond, that sort of electrostatic bond that they have, sucking them together like a magnet, for all of those different atoms. You're going to need a lot of energy to do that. Because of that, you should, if you paid attention just now to what I just said, be able to make a guess as to which one of these would have a higher melting point. So do you think the melting point of a plastic, covalently bonded solid, or a salt, an ionically bonded solid, is going to be higher? Which is going to be harder to melt? Which will require more energy to melt, to change from solid to liquid? All right, I see some good guesses here. People on both sides, or even someone put C in here, so maybe that's all. It's three sides. Superman is melting. It's a sad thing. No more Superman. Well, Superman will melt, at least this plastic one, at 100 to 300 degrees Celsius. Just a little warmer than, well, a bit warmer than room temperature. But salt, you're going to have to, if you actually want to melt it, you can dissolve it, but that's a different thing. Dissolving it is different because you're still not necessarily separating the sodium from the chloride. To actually melt it, you're going to have to heat it up to 800 degrees Celsius. Extremely hot, hotter than fire. So to melt an ionic compound, again, remember, you have to break the ionic bonds. You actually have to separate the ionic bonds there. But to melt a covalent compound, you don't have to break the covalent bonds. You just have to separate the neighboring molecules from each other. So just think about that when you're thinking about these trends, like things like melting point, that kind of thing, when we're talking about molecules. MSR? What? I don't know what that means. Wait, I know you're thinking, because you're really astute students. Teacher, you're lying to me. Because diamonds have a high melting point. They're at 3,500 degrees Celsius. But they're covalently bonded, right? Because they're just a bunch of carbon atoms that are connected to each other. I know what you're thinking. I know what you're thinking. But that would be slightly different because melting a diamond is not necessarily okay. Oh, I think someone's delivering a couch and they just set it up against our garage door. Melting a diamond is not necessarily a physical change because it is not about it's about breaking the bonds, not just about changing or separating molecules. Sorry. So, for example, we just have to separate the nitrogen molecules from each other. We don't have to break the covalent bond. The same is true with carbon. Actually breaking that covalent bond in the nitrogen or in the carbon is going to take a lot of energy. It just so happens that basically a diamond is one giant molecule. It's a connection of carbon atoms that keeps going and going and going forever and ever with covalently bonded carbon atoms sharing electrons. And that's why to melt a diamond, you're not actually just having to separate molecules because you've already separated. It's just one molecule. You have to then break the chemical bonds, which takes a lot more energy. So again, that's kind of more like breaking the ionic bonds, which is why it has such a... You did, Shay, I saw that. Low melting point. So now we're going to look at some of your projects. And I'm going to show you some of these, partly because I want you to see the projects, and partly because you worked hard on them, and partly because I think some of you can do a little bit better for next time. Now, what I mean is I was really impressed with what most of you put down for your text, for the things, you know, the actual like information and stuff like that. But I was not very impressed with most of you for the sort of, kind of sprucing it up and making it an attractive and interesting project. And let me show you what I mean. Oh, yeah. And two people. Who are those two people? Guinevere is one of them. Let's see, where's my list? I don't even know where my list is. But I might as well tell you who the two of you are right now so we can resolve. Two of you I wasn't able to give a grade to. And that would be Guinevere and you know what I'm going to do is before I show the grades up on the list is I'm just going to pause the screen, so I guess because you guys don't want to see each other's grades probably, huh? Or I could potentially get in trouble for that. Guinevere and Given, I wasn't able to view your prezzies, so you need to make sure that they're shared with me or they're in a way that I can view them or shared or just generally like available for people to view. So Guinevere and Given. All right. No problem, Bob. I know your name's not Bob. Well, you definitely sent me the link, and I have the link, but I can't view it because I don't have the permission to view it, even when I'm logged into Prezi. So you have to make sure that it's globally available for people to look at. All right, Given wants to be called Bob from now on. Just remember that, everyone. Hey, isn't Bob, that's the name of that minion, right? King Bob, something like that. So I want to show you, first of all, a couple of projects from last year. I'm not sure why, but I had some people that were willing to take a little more risk, I guess, last year and be a little more creative. So this is one thing. This is like a Facebook status that one person did last year. So it's like where I live in nature, status update. Hey, I've been discovered, blah, 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 blah. Work experience is like, what the different isotopes do or different things that, that kind of a thing. Jake Ritters, oh, you don't want to see that one, believe me. No, just kidding. So that's kind of something you could do, that would be a little more interesting. Then have maybe some photos of yourself. Oh my goodness, we went through a bunch. Here's another one where someone just included a bunch of fun facts about gold, which are kind of, it's just kind of, it's a little bit, it's sort of like extra, but it's also like showing me that you're really getting into it and learning about your element. And then obviously you can see here are quite a bit more images and pictures of things like helium might be used for in this case. Whereas for most of you this year, I noticed that it was basically just, here was one that had a picture. You can claim yours if you want. In fact, you can even say some fun thing that you learned about your element if you want to chat it, or I could even give you audio privilege if you want to do that. My screen's frozen. Oh, you're right. You guys are so smart. You guys keep me honest. Now you should be able to see it, right? Sorry about that. So this would be the project that I mentioned about, using sort of like a Facebook page for argon, and a little bit of a creative way of. And I think this is one of the Prezi things you can do, is kind of something like that, and adding a bunch of things to kind of put your information in that framework. Make it a little bigger. No, that's as big as I can make it. I'm sorry. And here's fun facts about gold, as I was kind of mentioning. And then here is the one pictures the uses of helium. So you can see that someone's really making a lot of use of pictures. I think that's really helpful to show me that you're engaged, and also that you're thinking about not just what do I know as a student, but how can I explain what I know to other people in a way that's going to make them engaged, interested, etc. So here's one of yours. Again, you may claim, if you'd like to say a fun fact or something you learned as you were studying your particular element, feel free to speak up and even do so if you want to turn your microphone on. Anyway, this is bismuth. I really like this picture. It's a nice picture this person found. I believe this is, well, I don't know if they want to say their name, but yeah, I think this was Sam's. And yeah, you can see it has this really interesting multicolored crystal structure. Now, in case you think that I didn't tell you about this, I mentioned it in class, and then also said add information and pictures to each of the slides, right? Well, you don't have to put a snapshot, but you can just look for images online, copy those images, and then put them into your, just do a image search or something for, if it's helium, you could show a helium balloon or, whatever it might be. Something like that. Or the Large Hadron Collider, where helium is used. All right, so here's some more. This is francium. I thought this was a really interesting fact, which I did not know at all until I saw it in this person's project. But only 20 to 30 grams of francium are in the Earth's crust at a single time. Isn't that crazy? Like the whole Earth, there's only 20 grams of francium right now. So we make francium in a lab, but it's this person showed, the last naturally occurring element discovered, and then we can now create it also in the laboratories. But it's part of a breakdown of radioactive uranium and plutonium and things like that. Pretty interesting. Oh, nice. Did you know, Sam, that gold, I think this is true, the total amount of gold in the entire world is just enough to fill an Olympic-sized swimming pool with gold. And that's all there is. We haven't found any more than that, which seems odd because we have all these, gold-like rings and stuff like that. But it might actually be true because Olympic swimming pools are pretty big, first of all. And then second of all, these rings don't actually have that much gold in them. It's sort of like an alloy of gold with other things. So, yeah. Anyway, I thought that was interesting. So if that's true, then bismuth would be 2 Olympic-sized swimming pools, I guess. Chlorine, a deadly gas. But again, as we just mentioned, chlorine, when you combine it with an alkali metal, like sodium, becomes stable. Sodium chloride, table salt. Because it's so greedy for electrons. Oh yeah, francium is an alkali metal. Yeah, so it's the heaviest one. Yeah, or else gold plated. That's right, Joel. Yeah. Potassium. Whose is this? I know whose this is. This person at least tried to use Prezi, and they did put some. This person actually did put some images in and all kinds of stuff, which I appreciated quite a bit. Great friends with all electrons except one. So potassium, again, one of those violent metals trying to get rid of their outer electron. Carbon. This is an interesting fact, I think, about carbon. There are two ways that carbon can be structured is diamond and graphite. And carbon is it is the hardest material known, whereas graphite is among the softest. Both just made of carbon. Carbon is a very, very useful and very, nice job, Shay, and very versatile, I guess we would say, element. Now, part of the reason I'm showing you this and encouraging you to try to adopt a little more creativity next time is because, first of all, it might grade a little harder next time if there aren't images and some effort made to be creative. And there is a next time. That's the reason. Because there's going to be a molecules project that you're going to do in a couple of weeks that'll be similar to this one. Here's another one. The discovery of, in this case, helium. Named after the Greek word for the sun, because that's where we first saw the spectral line for helium. And finally, last one, copper. Of course, very important metal in tool making and things like that. During the Bronze Age, copper is part of how you make bronze. So until the Iron Age, until we learned how to manipulate and use iron and steel, copper and bronze were the most important metals for tool making and things like that. All right, that is all I got. End of slideshow. Click to edit. So look at that. We're done with 6 minutes to spare so that Shay or whoever it was can go to their dentist appointment. Good luck at the dentist. Who's going to the dentist? I forgot. Yeah, it wasn't Shay, was it? Who's going to the dentist? Fess up. You know what? I bet that person is already gone. And they're in big trouble because they should still have 5 more minutes. Nobody remembers who it was? Oh, it's the doctor. That's right, Taylor. You're right. And you're here and you're paying attention, and I'm the one who's wrong. So now look who's in trouble. All right. Well, thank you all for coming. I'll see you guys next week. I'm sorry I've been a little bit behind on grading, but I'm trying to catch up. It's hard trying to be halftime and still, get all this work done. Anyway, you guys are great. Thanks for being engaged in class today. Have a good week. See you on Wednesday.